this session is Kazuya Yasuda from Tokyo University.
Good morning, everyone. I'm Kazuya Yasuda. I'm studying at the University of Tokyo. And I'm here to talk about the quantum process calculus and equivalence relations between processes. By using our new equivalence relation, we can formally prove some intuitively equivalent processes are equivalent in quantum process calculus. My presentation will be in 5 parts. First, I talk about the background and motivation of our research. Second, I review the definition of a quantum process calculus named QCCA. Third, I introduce an existing equivalence relation, which is named open Bayesian relation. And fourth, I define our new equivalence relation, which is named observational equivalence. And to define this equivalence, I also introduce 2 notions, schedulers and strategies. And finally, I summarize our research and mention future work. So please hold your question until the end. Okay. Now I will talk about background. Sorry. now I will talk about background and motivation of research. Many quantum communication protocols have been proposed and studied. This includes quantum key distribution, like BBH4, and quantum bit commitment, and quantum obedience transfer. However, proving the correctness or the security of these protocols is very complicated or error-prone. So, quantum process calculus, like QPLC, CQP, and QCCS, have been proposed and studied. So, how do we prove the correctness of the processes using quantum process calculus? First, we write a process which models the protocol by using the language of quantum process calculus. Second, we define the specification of the protocol and write it down in the quantum process calculus. And then, if these processes are behavioral equivalent, then the correctness of the protocol is proved successfully. So, equivalence relation between processes is very important. There already exists some equivalence, like Bayesian ratio and Barb congruence. However, there are some processes that are not Bayesian but intuitively equivalent. This slide shows an example. Consider these 2 processes. One sends a qubit whose state is 0 or 1 with the same probability, and the other sends a qubit plus or minus with the same probability. These states of qubits cannot be distinguished because the same decimal matrix expresses these qubits. So we intuitively think that these processes are the same. This identification is also used in Shor and Prescue's security proof, or BBH4. In order to formally prove these processes as equivalent in process calculus, we want to prove that these 2 processes in this slide are bisimilar. One measures the qubit whose state is plus, and then follows an arbitrary procedure. And the other applies the super operator E E is described in this slide. And after that, follows the same procedure. We want them to be equivalent. However, they are not bisimilar. So in order to regard them as equivalent, we define new equivalence relation on QCCS. QCCS is a quantum process calculus, and there are some notion of equivalence, which weak bisimulation, weak open bisimulation, and reduction bound congruence. Note that these three do not regard our motivating examples as equivalent. Okay, so far we've seen the background and motivation. Now let's move on to look at the definition of a quantum process calculus, QCCS. First, I'll show you the syntax of QCCS. In QCCS, we can express both classical and quantum behaviors of processes. This slide shows the classical behaviors, like sending or receiving classical data, non-deterministic choice between two processes P and Q, and parallel composition of P and Q, and conditional execution. The next slide shows quantum behavior, like the receiving or sending qubit, or applying superoperator E on qubit, and measure the qubit Q and towards the outcome of the measurement to the variable X. Then I show you the semantics of QCCS. States of processes are expressed by configurations. Configuration is a pair of a process P, with, as I mentioned before, and the quantum states rho. In QCCS, quantum states are presented by density operators. And transition or execution of process are expressed by the radial transition system. In this system, these notations are used as labels. When a process sends or receives classical data with using classical channel or connection C, then the first notation used as label. If a process sends or receives qubits using quantum channel C, then second notation is used. And otherwise, the tau is used as the label. Here, tau means an internal transition which cannot be observed by any other process. Okay, I show an example of quantum process. In this process, at the beginning, this process has two qubits, Q and R. Q state is plus and R state is 0. And first, this process first applies the gate C0 on two qubits, Q and R. After applying C0, the process becomes this state. Q and R are entangled. And applying this application of C0 cannot be observed by any other process or outside process, so we use tau as the level. Then this process sends qubit R using the quantum channel C, and this is sending qubit is an observable action, so we use this as the level. And there is another example, measurement. This process measures the qubit which states plus. And as you know, when we measure this qubit, we obtain 0 or 1 with the same probability. So transition of this process is like this. This example shows that the transitions of quantum processes are probabilistic. So we have seen the definition of QCCS. I'd like to introduce existing equivalence notion, which is open batch relation. Open batch relation is an equivalence relation between configurations. If two configurations, P, rho, and Q sigma, are open batch similar, then following four conditions hold. First, two processes have the same quantum variables. Second, the environment is which are the quantum state of all qubits, except they are the same state. In other words, partial traces of rho and sigma are the same. Third condition, for any transitions of P, there is a corresponding transition of Q. And here we can add or remove any tau transitions, non-observable transitions to Q. And we use this notation as the largest open batch relation. Okay, now I'm back to our motivation. We want to regard them as equivalent. When we write these processes using QCCS, then we obtain these two configurations. We want to regard them as equivalent even if we put any processes in these squares. But for instance, for simplicity, let's consider only these processes. After the measurement or application of E, J use the channel C or D. This choice is non-deterministic. We can prove easily that these two processes are not open batch similar. So we want to define new equivalence relation which regard these processes, these configurations are equivalent. So how should we define this equivalence relation? Now I'll talk about it. First, let's consider when two processes are equivalent. We thought that they are equivalent if they are observed the same by any attackers. Here, observable action is only receiving or sending data, and we think that attackers also can express by the process, quantum processes. So, in other words, two processes are equivalent if they use the same channel with the same probability whenever they run parallel with any other processes as attackers. There are some similar notions of our equivalence. One is verb congruence. This notion is already defined in QCCS, but this verb congruence coincides with the largest open batch relation, so we cannot regard motivative examples as equivalent by using verb congruence. And another notion is testing equivalence. This notion is not defined in QCCS, so we want to define this notion in QCCS. Okay, now in order to define this our notion of equivalence, we must consider the probability of using each channel. Defining such probabilities is not easy because quantum processes have non-deterministic transition. This slide shows an example of such a process. In this process, three sub-processes run parallel. There are two non-deterministic choices. First is if the left and the middle sub-process communicate, and after that, this process can use channel D. And otherwise, if the left and the right sub-processes communicate, then channel C can be used. In such a situation, how should we define the probabilities of using each channel B and C? To solve this problem, I introduce the notion of schedulers. Schedulers solve non-determinism of transitions. That is, they choose one of the non-deterministic transitions for each configuration. For example, let's take this scheduler F. For this configuration, scheduler F choose this transition, not this transition. According to F, this process can use the channel B with probability 1 and channel C with probability 0. Similarly, if we use this scheduler, then it can use only channel C. So to use schedulers, we can define the probability of using each channel. So I plan to define our equivalence relation. We name this new relation observational equivalence. Two configurations, E rho and Q sigma, are observational equivalence if these four conditions are satisfied. And first and second condition are the same as open by simulation. And third condition is what I mentioned before. That is, two processes use the same channel with the same probability whenever they run parallel with any attacker. Here, we regard this process R, arbitrary process R, as attacker. So I showed the sketch of this notion. These two figures are the image of transitions of configurations. I showed that these two configurations are observationally equivalent. First, fix a scheduler of the left process, like this. In this case, there is a corresponding scheduler of the right, and they use the channel C and D with the same probability, each one half. Next, fix a scheduler like this, and similarly, there is a scheduler, corresponding scheduler, and in this case, they cannot use any channel. If they run parallel with any process R, and we can check this, we can check the same conditions. So we conclude that they are observationally equivalent. Okay, we have seen the definition of observational equivalence, and now let's back to our problem. As I talked before, we want to regard these configurations as equivalent, but they are not open by simulation. However, they are still not observationally equivalent. Why they are not? This slide shows the reason. These figures are the transition of the processes. For this scheduler, using channel C with probability 1, they are corresponding one. And for this scheduler, like this is corresponding one. However, if we consider this scheduler using channel C with probability 1/2 and D probability 1/2. So there is no corresponding scheduler of the right process. So they are not observationally equivalent. Now I thought why they are not equivalent by using observational equivalence. We thought this is because schedulers can choose different transitions after the measurement. This slide shows such a situation. Schedulers choose the different transitions. However, these processes don't use the outcome of the measurement, so their process is the same. Then we thought that schedulers should choose the same transitions if the process is the same. So we defined a new notion, which named strategy. Strategies are the limited schedulers. That is, strategies cannot choose different transitions if the process is the same. By using strategies instead of schedulers, we can define similar observational equivalence. We named this relation, this new relation, observational equivalence with strategy. Now I'm back to our motivating examples again. These are intuitively equivalent processes, but however they are not similar and they are not observational equivalent using schedulers. But we proved that they are observationally equivalent with strategy. So I conclude that the observational equivalence with strategy is what we want to define. Now I mentioned the relation among these equivalences of bisimulation, observational equivalence with strategy. We at first accepted that there is inclusion relation. But, however, we found that they are incomparable because we can write specific configuration such that here, here, so they are incomparable. Up to this point, I've talked about what we did. So let's move on to summarize what I've taught. In my presentation, I reviewed the definition of PCPS and overbisimulation. Next, I defined two observational equivalences. One uses schedulers and one uses strategies. After that, I compared them with overbisimulation. In conclusion, observational equivalence with strategies because our motivating examples are equivalent. In addition, these three equivalence relations are incomparable. So here, the question is, which equivalence relation of three is really most intuitive? In the motivating situation, we can say that the observational equivalence with strategies is the most intuitive. But if we consider another cases, other situations, it is rarely intuitive. We think that these examples are artificial, are natural, but it remains the room for argument about this. In order to solve this problem, we must formalize our intuition first, and then we can discuss whether equivalence relations are intuitive or not. In addition, we should discuss about congruence properties of observational equivalence. The property for file composition are obviously by definition, but we didn't discuss about other contracts, so this is one of our features. Thank you for your attention.
Okay, there's some time for questions, comments. Yes.
I'm interested to know if you have an idea how you would formalize your intuition.
So this is very difficult.
Yes.
So we don't know what it is.
So which parts of this work can't be done in the classical computation?
Sorry, what do you mean?
Which parts of this, how does the fact that you're working with quantum computation affect this? Which parts of what you've done can't be done with classical computation? I didn't see where the fact that you're working with quantum computation really affected this work.
And so So we try to do this example. Sorry. I try to figure these processes as equivalent, and this example is a quantum one because quantum measurement have two notations, which is to measure the qubit and obtain classical data, and trying the corresponding total operation. So this problem is raised because we think about quantum situation. So answer your question. Okay.
Yes.
So you said strategy is limited. Strategy is a scheduler with limited capacity, right?
Yeah.
Could you repeat again what is exactly this limitation?
Yes. Strategies is scheduler, and the limitation is when two processes are the same, exactly same,
Yeah.
then they choose the same, they must choose the same transition.
So no matter what the history is, if it sees the same term, then it has to choose the same transition.
Yes.
Okay, I see.
Scheduler and strategy both regard the history of transition.
It sounds like a pretty strong limitation.
Yes.
And like, for example, like, have you found any similar limitation or assumption in the context of concurrency theory?
Sorry, I can't answer the question.
Okay. Yeah.
Thank you for your chance.
Any other question or comment? Okay, then let's conclude this session. Thanks again to speakers.
Thank you very much.
Is there any announcement? No? Okay, just lunch and come back.